Okay. Hello. Please welcome our next speaker, Adam Miller from Fedora Engineering at Red Hat, who will be talking about deploying OpenShift build service, aka OSBS.
Thank you. Clicker, ha. Okay, so I want to talk about first what the presentation is going to be about, the format we're going to go in through, and if any of this does not look interesting to you, please feel free to go find a talk that is interesting. You will not offend me. I want this to be fun for everybody. I'm going to start off by telling a fun history lesson, a little bit of a narrative of how this came to be in the Fedora space. Lessons learned there, which is kind of the premise for the talk. From there, I'll go a little bit into the technology involved. I want to take a quick moment to define what containers are and what we mean by container build images and layered images versus base images. I'm going to very quickly go over what is OpenShift and describe it from an architectural standpoint and why that is important. I also want to define what release engineering is because that will provide context around why certain decisions were made the way they were, the way that why the image build system was designed as it is, and then actually go into what OSBS is, the Koji container build plugin, and Atomic Reactor, and how those all kind of feed into and power what became the layered image build system. So, the history lesson. Once upon a time, a very long time ago, like 18 months, not that long ago, Matt Miller, the our fearless leader, randomly said in a meeting somewhere, he's like, hey, so there's this open source layered image build system. We should deploy one for Fedora. I don't remember the exact quote, but that was roughly the paraphrase. And what the misconception was is that this was a finished product that somebody had done and released upon the world and was ready for use. So we kind of sat around and kind of talked about that and looked over the architecture design and discussed it from a high-level abstract. And we said, probably going to take about 4 weeks to accomplish. We need to, first deploy it in stage. We need to figure out where the integration points are for our message bus, for our build system, make sure it ties into our testing pipeline, our release tooling, that kind of stuff. 4 weeks. And this was an incorrect assumption because the layered image build system and its various components were rightfully so following the release early, release often. So this is what actually happened. We started off with a whole bunch of GitHub issues and tickets, and in the early time when we were not yet familiar as a Fedora group, we were not yet familiar with the code base, we were just frantically submitting issues because we had no idea what was going on and why nothing was working the way that we thought it was going to. It wasn't so much that it wasn't working, it's that we were trying to introduce new use cases or new workflows to the environment that the team that had originally written it had not taken into account or were not necessarily targeting. So what I kind of flipped through here, wow. That jump. Okay, so we have a bunch of issues mixed in there, our pull requests, more of those, yay. And we have a production environment now. And so we actually released just this last December, so it's been live for about a month now. So phase 1 was the single node builder, and this was finished last November. And I don't mean like 3 months ago November, I mean a year ago November. And it went pretty well. It went pretty quickly. Things worked. However, then image format v2, registry v2, and manifest v2 happened, and this broke the original implementation. And the reason for that is because fundamental components of the API or the specification for the image changed, and they changed in non-backwards compatible ways. And then actually during the journey of refactoring and reorienting the build system to handle these, more changes happened that were also incompatible. But because of the fact that the changes to the architecture and the code had been made to cater to the fact that we were broken previously, it was much easier to pivot this time and pick up these changes because we did not collectively make similar mistakes of relying on fundamental truths to remain true. Because we got bit, what was it? Once bitten, twice something? I don't know. Anyways, I forget the saying, but we tried very hard not to make the same mistake twice. So phase 2 was the scale-out deployment, and this is what finished in December. and what we were able to get out and publish to the community such that people can start building containers. And for those who aren't familiar, the Fedora Atomic Working Group, which is focused around all things container, atomic host, container running technology, container orchestration within the Fedora project. We are going to host our first virtual Fedora Activity Day this coming Thursday. Yes, this coming Thursday. And we will actually be moving, I think our initial goal is 50 container images from the current Fedora Cloud GitHub working space into the official Fedora build system. So we have all of that done. It's fully compatible with all the new stuff. We can run it on the latest versions of Docker and run C and anything that can do OCI compatible images. We have automated tests currently in staging. That's going to be going out to production very soon so that we can actually automate the pipeline. And then we have the ability to promote images to production release from there. In the future, we want to do image registry scale out. So right now, our registry is not as scaled as we would like it to be. We're going to create a front-end endpoint and allow multiple registries on the back end to answer for registry.fedoraproject.org. And this will give us more site reliability. And we're also looking into ways to handle GeoIP. So when you do a pool operation on an image, you can get a local instance of a registry or a local mirror to get the content from something that's geographically close to lower download speeds, latency, those kinds of good things. Search and advertisement of images. There are very few options for searching and advertising images out of a registry, and 0 of them are native to the registry. So each one has kind of that fear of the future where something will change again, some fundamental truth that we once accepted to be true will be removed out from under us, and we'll have to pivot again. So that's being discussed, and we're going to have that coming up very soon. And then we're also trying to figure out a good way to do CVE and security metadata release and distribution. So when you're on your Fedora or system and you use DNF, or if you're on your RHEL or CentOS system and you use Yum, you can check security info. You can do update info and check security and see CVE data and read about change logs. Right now, there's not any way to do that for Docker or any of the OCI runtimes. But Docker pull and Docker search being kind of the de facto standards in the community space for those kinds of things. And it's difficult because this is a desired feature, but we want to find a good balance of doing it without trying to lock anybody to a specific tool chain and have a good way. So that's something we're trying to figure out as well, because we absolutely want that. It's just an interesting problem space, and anybody who has a suggestion for it, please come participate in the Atomic Working Group, because it's basically an arbitrary pile of metadata attached to a tarball with some JSON, and there's no concept of versions or releases, and we're trying to kind of define abstractions for that. So, lessons learned. I want to take 2 line item moments to tip of the hat and say some thanks. So the upstream OSBS team is fantastic. In the first few months when we were doing this, and we had no idea what we were doing in terms of trying to touch the code base, because there's a pretty respectable amount of code involved in all of this, we were just frantically running to them, thinking the world was on fire and everything was just falling, the wheels were falling off the cart kind of thing. And again, we later learned that it wasn't the wheels were falling off the cart, it's that we were trying to make the system do something that it wasn't originally designed to do. So we kind of dug in and got to roll up our sleeves and learn the code and started to try to contribute patches. But aside from that, they were very gracious in originally taking on more work to cater to some of the early requirements for the system. And we want to say thanks for that publicly. Also, OpenShift team, we had a similar scenario with some of their stuff. There was a lot of the work was targeting sets of containers and network components that weren't necessarily all that stable yet in Fedora, and all of our build system stuff runs on Fedora. So just want to say thanks, because they were very responsive to, again, us running to them and saying, oh my gosh, the sky is falling. So OpenShift is really powerful, and what I mean, and I don't mean that to be just kind of like some weird underhand. I'm not trying to like sell you anything, but it was very fascinating to actually get to a point where we were deploying a system that had the ability to have a custom build specification, and you just have this pile of JSON and some YAML files, and you throw it at the system, and within the cluster, it would provide you everything that you wanted out of it, and that was just kind of really cool. But also with that power came a little bit of a learning curve, trying to figure out how to handle that as a new workflow, how to handle the system. And I'll actually, I have some slides a little bit later on that kind of explains what OpenShift is, and I'll have a little bit more specifics on examples of how that was. So for those who don't know, I used to work on the OpenShift team, but when Architecture v2 was a thing. So I had actually moved over to the Fedora team around the time that Architecture v3 was being hammered out, and they were starting development on it and basically rewriting everything and basing on Kubernetes. So it was a huge learning curve for me, because it went from this Ruby broker-based thing with SE Linux sandboxing and their own implementation of C groups management with mCollective, and now all of a sudden it was Kubernetes and all these things. So it was really cool to learn how the build pipeline worked and be able to integrate that into the build system. Another thing that we learned almost in a trial by fire is that the container ecosystem moves fast. Nothing is guaranteed, nothing is set in stone, because of the fact that the environment, or I guess the underlying technologies that for what I'll consider a traditional application runtime, they're pretty standard. They're pretty set. There are certain components about the system or certain things about general, GNU Linux distributions that you can kind of rely on being kind of stable. None of that is true in the container space. Everything is constantly evolving, and it's very exciting. It's very fun to be a part of, but it's also very difficult to track when you're trying to build something. So we learned kind of the hard way that APIs are not always going to stay stable, and they will not always stay relevant. There was a certain point in time where there was an announcement about an API specification change, and we had 3 months to update, because the old version was going to no longer support, the old version of the API was no longer going to be supported by the upstream. So yeah, and don't expect backwards compatibility. That's kind of the follow-on to that, like breakage in API. There was, at some point, there's a cutoff where image v1 just was a thing of the past. So containers, really quick, what are containers? Kind of talked about it from an abstract, talked about building them, but what are they as a thing? Operating system virtualization, and if anybody attended my talk last year, actually, this is a repeat slide. Mostly because I'm a huge fan of it. I borrowed some of the content from some other people much smarter than I, and I've been trying to kind of level set what it is, in the sense that a lot of people out in the ecosystem have, I guess, what I would call like a marketing opinion of what containers are. But they're basically operating system level virtualization. It's the idea of multi-tenant isolation, the ability to present an environment to an application runtime such that it thinks that the environment which it exists is a system. It has a root file system. It has, various libraries. It has the various utilities that it needs. It can, for whatever reason, inspect the process tree or proc file system however it wants to, but it's not a full system. You couldn't boot it. Most times it's going to be lacking things. Probably doesn't have an init system in it. Those kinds of things. So containers are not new. They've been around for a long time. I always like to argue that the chroot was the original container, in the context that you can lie to the application runtime, and it will execute and run like it would otherwise on a base system, but it is not. And the chroot was very unsophisticated. And there's a brief lineage of Unix-like container or operating system level virtualization technology. Whereas LXC was kind of the first thing in Linux that got really interesting. IBM released a tool chain that provided that. somewhere around 2011, systemd nspawn was created. And systemd nspawn, as I understand it, was just created so that the systemd team could test systemd without having to reboot systems all the time. It added a lot of sophisticated features that we didn't previously have. .cloud, now known as Docker Incorporated, then released Docker. A year later, CoreOS released Rocket. A year later, the Open Container Project, also known as the OCI, Open Container Initiative, happened. Started defining specifications because a lot of this technology was in a lot of ways trying to describe similar patterns, similar execution environments, similar images, but there was no real consensus around it. So a bunch of companies got together, including Red Hat, and are trying to standardize on that so we can get to a point where we have these image formats and these APIs that are stable and bring some cohesion and I guess stability to the different areas. What was it, a year later? Same year? Yeah, same year. Shortly after the OCI was created, Run C came out. It's kind of the reference implementation of being able to execute images from the OCI specification. Then just this past year, Containerd came out, which is a OCI compliant daemon to kind of manage Run C execution runtimes. Sorry. So that was just a brief history to kind of give the idea or make sure that it is understood that there's not just one runtime in town. There's not one solution for this. And something that Fedora is trying to aim for is we're trying to aim for providing OCI compliant images such that our end users can run and use these images in any way that they choose. We in Fedora are all about freedom, all about friends. We are all about trying to be first, try to bring the new features first. So if we can provide the ability for our end users to run our images in any way that they can, all the better. But really quick, the reason it's called the layered image build system is because the idea is to allow Fedora contributors to maintain and build layered images much like they build RPMs today. But you need to understand first what the difference between a base image and a layered image is. So a base image is going to be the thing that provides kind of the core platform shim, for lack of a better vocabulary term, to a layered image. And that base component is going to provide things that you would kind of expect out of a containerized runtime that would come from a distribution. So probably going to be things like glibc and maybe a shell, bash. For the Fedora use case, probably DNF. Probably going to want a package manager in there, those kinds of things. So we'll provide that in as small of a package as we can. We want to keep that lightweight as possible. And then a layered image is going to build on top of that. That will add functionality for a specific use case. And let's just say, for example, you wanted a web server. You want a web server in a container. So we'll just say, Apache HTTPD or Nginx or, I don't know, Lighty or I don't know what's cool these days. We'll go with that. Apache. I'm going to stick with it. So you can run Apache, and you would basically have, a build configuration that would say, I want to add Apache to this, and I want to be based on a certain layer. And what's interesting about that is because this actually enables the ability to decouple our desired runtime from our base platform operating system. So we could potentially run a piece of software from Fedora 24 inside of a container on Fedora 25. And what's cool about that is if you're running certain application stacks, let's say Ruby on Rails or Node.js or Django, some framework for something, and there's a giant leap. So there was I think it was Rails 3 to 4 a few years ago, Ruby on Rails 3 to 4. Very non-trivial for most people to port between the major revisions. And this kind of thing would have made that transition period a lot easier because you could go ahead and upgrade to the newer operating system, take advantage of the new functionality, the new speed increases, the new kernel support for the various things, new libraries and that sort of thing for the host, but you can go ahead and bring along your new image. So what we're targeting here with the layered image build service is the layered images. Fedora release engineering provides the base image, much like we provide ISOs and cloud images and those kinds of things, and then contributors throughout the community will add to that. Also, a side note, Fedora release engineering isn't some kind of like weird closed room cabal. It's all open as well. We have community contributors there as well. There's just a little bit more structure in the tool chain for what the base image is produced. So OpenShift, really quick, OpenShift is a container platform built on top of Kubernetes, has advanced features such as build pipelines, image streams, application lifecycle management, and various other things that are great for developers. The piece that we care about is build pipelines. There is a concept in OpenShift of a build. It's kind of a primitive data type to OpenShift. It provides the ability to use pre-prescribed build strategies, or you can provide a custom one. We do a custom one. So this is kind of the huge layout. In the green section, second from the bottom to the left, the build automation, that's the piece we care about. Fedora, we run OpenShift Origin, that's the upstream project for OpenShift. That's where we participate. This is the basic architecture overview. It's effectively you have your client talks to the REST API. There's a scheduler on the master, and the master talks to the nodes. Inside the nodes, there are pods, and inside the pods are multiple containers. And the reason that's important, or at least noteworthy, is because this architecture, and by using OpenShift, we have an ability to actually scale our build system pretty easily. So we use Ansible to deploy the entire build system internally, and at any point in time we realize we are low on capacity. All we need to do from an administrative standpoint is add nodes to the inventory and rerun our Ansible playbook, and it will provision more capacity for us. And that would be the nodes. So we'd provision more nodes. So release engineering. What is release engineering? I want to go through this very, very briefly just to kind of explain why some of the things that we do are the way that they are, instead of just saying, run Docker build on your laptop and ship it, because why not? So making software in a production pipeline that is reproducible, auditable, definable, and deliverable. And the auditable and the definable components, I think, are important as opposed to the other ones, because, reproducible and auditable. Definable and deliverable you can do on your laptop. But the reproducible and auditable are the components that we care about, so that we can make sure to have a well-established trust chain with the user base. So when we say that we've shipped something and it contains these things, we can verify that. So layered image build service, OSBS, OpenShift build service. So what the OpenShift build service is actually a loosely coupled set of components. The main one of it, which is the OSBS client. And the OSBS client takes advantage of the OpenShift build pipeline by creating a custom build strategy. And we have this build configuration, and it defines the inputs that we must provide. On top of that, it also provides a Python API, and that Python API is also presented to the user as a command line. So you can enter the inputs that you want through the command line, or you can do it via the API. And we chose to do it as the API so we can automate it programmatically, those kinds of things. OSBS enforces the build inputs. If you attempt to do something you're not supposed to, it will fail. We have a build route, which currently is a limited Docker runtime. We're also toying with prototypes of other runtime backends for the build pipeline, and trying to again explore more of the container ecosystem, find things that are more performant or that are potentially more performant, make sure that we're providing the best solution we can. So it is firewall constrained, and we also have input verifications as far as input sources of content. So if you do a Docker build and you read Stack Overflow, I don't know, because it's 4 in the afternoon, you haven't enough coffee, and you're just, Facebook got boring. And somebody's like, hey, you should just curl pipe this to bash as root. You're like, sure, that sounds like a great idea. Let's slap that in a Docker file. And then let's ship it to Fedora users. And while that is debatable as a deployment install strategy, the problem comes in is the verification and the reproducibility. Because let's say that the point that you did the curl from disappears. At the end, we resulted with basically a source input that says curl this thing, pipe it to bash, and that's going to do some stuff. We might have some build logs, but we lack the ability to audit the trail of content and find out where that came from, what it's actually doing, because we may never have stored the actual install script. So those kinds of things. So if you attempt that curl pipe to bash inside of our build root, the build will fail because the input source would not be verified. We use OpenShift image streams to detect the input sources to a build root, so anytime things happen there. And this is actually going to be the kind of the inflection point in the future where we will do automated rebuilds. So in the event that we update the base image, things that directly need the base image will automatically be rebuilt as layers. So let's say, for example, you're building or you want to put WordPress in a container, and you started that WordPress off of maybe the PHP container. So you're not directly depending on the base image, but at some point you will. In the event that the PHP container were to get updated, then the inside of the build system would know to cascade up a build to the WordPress and those kinds of things. So while that's not, as it is today, that work is underway, and we'll be getting there soon. We're also going to have a Factory 2 component. So for those who have heard of Factory 2.0 or have seen the Factory 2.0 talk, there will also be a component of the build environment that will have a record of all of the content that's going to go into a layered image, and then in the event that there is an update noticed within the Fedora update system, and it would then require, there will be a manifest of the RPMs for a layered image build service, or a container layered image. And in the event that one of the RPMs that go into that layer gets an update, the system will automatically notify the various tools that need to and update them. Because right now, we basically just need to update the base image and then cause cascading rebuild, which will then pull that in, and we do that on a regular cadence, except when there's a security update. Then we do it. We break cadence and we get it out as soon as possible for the security update. So. Atomic Reactor. So inside of that build root that I talked about, there's a component called Atomic Reactor. It's a single pass build tool. Does all sorts of really, really cool stuff. It's got a pile of plugins. We wrote some of our own. And this is what allows us to tie this directly into the rest of our environment. We're also able to gate updates. So again, we can promote images when it comes time. So all of the builds, as they go through our system, automatically land in a candidate registry, and you can pull them as soon as they're done building. You can test them. You can even, share them out with friends and say, hey, check this out. And then we will gate and verify. Once verification and validation happens, we can send it out. Something else to note is when a build completes, there's actually a metadata import that contains information about how that image was built, how the image was built, the sources that went into the image, and all of the content that is within the manifest that is in that. And given that, we can actually reproduce, not bit, like we haven't mathematically proven that it will be bit for bit, but we can verify that the manifest name version release of every RPM that goes into an image can be reproduced, and each of those RPMs themselves can be checksummed and verified because they're signed and all that. So anyways, so this is the system, and this is kind of why I wanted to mention earlier the OpenShift architecture, because in here it's just kind of like this box. You can't really see how well scaled out the environment is. But for those who are Fedora contributors, the idea of kind of coming into dist-git and putting in a spec file and then submitting a build to Koji and having have Koji build go through, and then you submit an update to Bodhi and that go out to the users, like that's pretty par for the course. You're used to that workflow. So what we did is we tried to mirror that as much as possible to keep this as consistent as possible for the Fedora users. So a layered image a maintainer comes in and they'll have their Docker file and potentially their service and init scripts and those kinds of things, and then tests and documentation. And instead of doing a Fed package build, they'll do a Fed package container build. And then that will fire off in Koji, and Koji will schedule that build inside the OSBS system, and then OSBS will perform the build and import. So the logs are actually brought into Koji on the fly, iteratively, kind of as it goes. And then when it's done, all the metadata will be imported. And then from there, a message gets sent out. So actually, I don't have this diagram. I probably should have. But from there, actually, a Fed message gets sent out. Taskatron will pick it up, and we'll actually be able to do testing and everything from the candidate registry before we distribute to the users. So dist-git, for those who are not familiar, this is a distro Git structure set up by Fedora. It's used to provide versioning for all the input sources that result in becoming Fedora. There's a branch for each release. Master branch is Rawhide. Rawhide is our development version, for those who don't know. Fed package is the maintainer's build tool. Allows us to have kind of some niceties for dist-git and initiate builds locally and remotely. If anybody wants to do mock builds locally, you can do that. Koji is Fedora's authoritative build system. Everything that we would potentially need to know is in Koji. And why that's an interesting point is because if at any point in the time we want to just blow away the entire OSBS system, we can, because we have one-touch deployment in the Ansible playbooks inside the Fedora infrastructure. And this is something we do in staging periodically just to make sure that it still works and we haven't broken anything. And because Koji is authoritative and it does contain all the metadata required to reproduce any of the layered builds, we can actually just remove it. And since it is disjoint from the registry, we don't actually lose anything. And since all the logs are imported in Koji, we don't actually lose anything. But I wanted to kind of point that out because it is interesting to note that Koji is where everything happens, not just for layered image build system, but also throughout all artifacts of Fedora. So RPMs, live images, cloud images, ISOs, the distribution stuff, things that you get on the little USB sticks at conferences, all that. Koji Container Build is the plugin that enables Fedora Fed package container build, the thing that allows us to actually do the integration point in Koji with OSBS, and then the registry is our upload destination. So I spoke really fast. So we're actually done. If you have any questions, I'll be happy to field them. If not, I'll give you a little bit of time back. I ran through this and it took me 40 minutes last time, and I did it much quicker. So. Yes? Okay, so the question was, are there hooks to get notifications upon build failures in the event of an automatic rebuild? Okay, so the question was, when an automatic layered rebuild happens because the base image changes, will you as a layered image maintainer get a notification in the case of a failure, or will those be validated in some way? Can you get feedback on the new rebuild? Just a notification period? So two things. One, you can, because FedMessage will be capable of that. We will have to define something that would contact you as an image maintainer. But two, you can't because the automated rebuilds don't fully exist yet. But that's something that we should absolutely do. I think that's a good idea, and I think it's good feedback in terms of something that would probably be useful to maintainers. But as far as validation, we will absolutely. So the Fed message will go out. Taskatron will pick it up and run the tests. So we actually have a document that kind of lays out how you should have tests defined within our environment so that they can be run. So we can at least, once the layered rebuild happens, get the test. And the tests will define what is released. So when we do the gated release, we will be able to query the historic test data, and we won't push anything out that didn't pass the tests. But yeah, so notifying you in the event of an automatic rebuild causing a failure is probably something we should look into. So not today, but we should. Yes? Take us through the process of the next shell shock and how long that will take. So shell shock happens. We'll call it shell shock 2 because I'm super inventive. That fix will go into the RPM. That RPM will go into Bodhi. That RPM will come out of Bodhi into the updates repository. Then automatically a build will be triggered. Well, okay, so today somebody in RelEng will go trigger a build. Hopefully in a few months, a build will automatically be triggered. That will go through and it will cascade rebuilds throughout anything that relies on it, which is going to be everything because that would be in the base image. Those would chew through, and as they come out of the build system, it would go through the testing and have verification. Right now, builds take on average 2 to 5 minutes, depending on how big of a task list is in the Docker file defined. Tests are going to again depend on specific images and what level of testing they require and all those things. So we'll say 10 minutes. And then once those are done, we can trigger an automatic release based on the latest tested. And those can be done in parallel. We can right now build 16 images concurrently, and we can scale up from that if we need to pretty quickly. Like within 20 minutes, we can add multiple extra nodes. Right now we're averaging 8 concurrent image builds per node, and we have 2 nodes currently because there are 5 layered images in dist-git at the moment, so we didn't feel the need to increase capacity yet. So I mean, that would be kind of the workflow. As far as time frame, a lot of it's going to have to do with how many layered images we have. So let's just guesstimate that we have 100 layered images. And if we divide that 100 by 16, we're looking at what, 32? You're making me do math. So 6. So yeah, we'll say so 6.2 times. We'll say worst case scenario 10 minutes per build. Which is potentially, realistic given the added load, and it's a little bit outside the average. So it would be an hour for builds, and then as they get done, kick off tests. So we'll say again, worst case scenario for 10 minutes apiece. So we'd be looking at potentially 2 hours once the updated RPM hits stable, and all of that uses the internal RPM repos, so we actually don't have to wait for the mirror network to update. So let's say 4 hours, just to be a little bit safe side, not lie too terribly. So 4 hours, we can probably do turnaround time on something like shell shock in the future. Yes. Okay, so the question was, how many image flavors do we plan to have, and what's the goal for the applications? So initially, this was kind of kicked off through the Fedora Atomic Working Group, which used to be the Fedora Cloud Working Group. We kind of moved towards the idea of targeting Project Atomic as our upstream and trying to deliver that across cloud platforms and native hardware. So the original target is to bring containered applications on top of the Atomic host as a runtime platform. As we kind of, but with the subtext that it doesn't have to run on the Atomic host. I mean, it can run on bare Fedora anywhere, realistically anywhere you can run OCI images. The goal or the initial hope is that we can deliver something that is very useful as a a server platform, either in cloud environments or locally for container workloads, whether it be single host or multi-host orchestrated. And those kinds of things. So the initial goal is this coming up Thursday, our virtual activity day, where we're going to move roughly 50 of various services that have historically been on GitHub and distributed through the Docker Hub. We're going to try to bring that into our build system and actually work on that. So it's very standard things like HTTPD, Nginx, PHP. Python, I believe there's a Python Flask, there's a Django, there's a Rails, like just kind of trying to get those application stacks or the in container images, our syslog, things that you would would probably want in an environment. And that's the initial goal. From there, I think a lot of it's going to evolve, but something that we're currently scoping out with the workstation group is Flatpaks. So one of the things that Flatpak is aiming to do is also being able to distribute their images as OCI compliant images. So if we can get there, we can probably integrate some of that with this similar build pipeline. Testing would need to be a little bit different just because of the nature of Flatpak, but we want to be able to leverage the work that was done here for some of the future things that we want to do. Similar thing with modularity. So the modularity group is hoping to distribute modules both as traditional sets of RPMs as well as images, and we'll have those in there as well. So kind of a lot. I mean, by a lot, I mean like spread out amongst different initiatives. But yeah, the initial goal is to target the atomic host and provide content for a useful, I guess a useful. What's the word I'm looking for? Just something like a useful solution for the problem or the desire of having a fully containerized environment for. So the question was, is something we want to do is ship Firefox in a container. So for desktop applications, for graphical environments, Flatpak is the preferred solution from a Fedora standpoint. So that is something that we absolutely target. We are aiming for that. I don't know how soon on the timeline that's going to be, but that is something we're definitely working towards. We actually, so the Fedora Atomic Working Group, a handful of members of us as well as members from the Fedora Release Engineering team met with the desktop team just earlier this week to try and come up with kind of a precursor plan for what work needs to be accomplished to allow exactly that. So allowing Firefox, LibreOffice, those kinds of things to be distributed as containers and run as a Flatpak runtime. Yes? Okay, so the question was, everything that I talked about in the scenario of shell shock was targeted on a Fedora released version, and the follow-up question, or I guess the follow-up question to that premise is, are we doing any of this release rebuilds or anything for Rawhide? The answer is not yet. That is something that we actually need Factory 2.0 to exist to power because of some of the kind of tracking of all of the, I guess the funnel of content coming into Rawhide. We need something to have an idea of what's going on there. And right now we're able to kind of get that from Bodhi, but there's no Bodhi for Rawhide. So yeah, so not yet, but that is planned. Like we absolutely want to keep Rawhide in scope. There was, yeah. Okay, so there was a comment and then a question. The comment was, right now with the Red Hat images, there's roughly 120, so that's probably a good estimate for, a relatively initial offering, since this is available and a lot of people in the Red Hat community participate in Fedora. We'll probably be in that ballpark pretty soon. The question was, for builds, are we hooking to things like Maven? And the answer is no, not yet. Right now, we're only doing RPM content allowable in Docker, in the Docker file for the image build. And we plan to do better for that in the future. The big thing is to track the ability to audit and reproduce the build. We need some way to curate that content stream. And with RPMs, we have that because we have that tooling, because we as a distribution have been doing that forever. But for things like Maven, NPM, Ruby Gems, you know, PyPy, Peckle, Pear, all of those things, we want to get to a point where we have that. We just don't yet. And but it is on the roadmap. So if you go, so on my last laptop sleeping, maybe Bueller. There we go. So I have a reference page. So once this talk is up in PDF format, or however they want, the DevConf folks would like it exported, on the wiki page for the initial proposal, down in there we actually talk about the future of wanting to do curated content. We just don't have it yet. Oh, I didn't mention Maven, but yes, Maven along with NPM and RubyGem and all those things, we absolutely want to do that. Yes? Retention policy for images. The question was, what is the retention policy for images going to be like? We are going to keep n and n-1. So whatever the latest release of a particular image and its previous release will be in the registry. We're going to continuously be cleaning out the registry because it's just a lot of data. And but we want to keep current release and -1 to allow for quick rollback, because that's kind of a big functionality, or a big new feature that we have that we didn't used to have, is the ability to atomically update our operating system with atomic host, and then also our application stack with, you know, the container images, because they're immutable. So yeah, so we'll keep the latest and -1. There's been discussions of possibly doing -2. And I mean, we can hash that out in the working groups as a community. We're open to it. It's just, to start off with, we figured current and -1. Okay, I believe we're pretty close to time, and I don't see any other questions. Thank you all very much.